This is one of the main things we need to sort of determine and remind you, because we've done digital electronics and we've done the basic principles. Now the next thing is analog electronics. Now, does anybody, I think I might have talked about it earlier last term, anyone remember what the difference between analog and digital signals are? It might be easier to think about it. What's characteristic of a digital system or a digital circuit?
Binary.
It's binary, meaning how many different states are there?
Two.
There's two. And generally it's either something is turned on or it's turned off, or it takes one of two separate voltage levels. Okay, so a digital signal, we might measure it as a voltage over time, probably the easiest way to sort of think of it. And a digital signal might just take one of two different states, so one or two different voltages at any time, okay? And so you can see over time it's turned on there for a minute and then it's turned off, back on, back off, and we can use that to encode some information into it. So for example, if we might have 4 wires all with digital signals on them, and that might be a 4-bit number. So it might represent a value based on the digital states of each of the wires and some encoding that we've given meaning to what those voltages on each wire mean. Okay. With analog electronics, we don't have just 2 different states. We have an infinite number of states that we can have, an infinite different number of voltages. Okay, and so it might take as a waveform, for example. So we might have a waveform that looks something like this, or it doesn't have to look like this. It could look like any mess you like, really. So another perfectly reasonable analog signal, it doesn't even need to be all positive, might be something like that. So that's complete. Very hard to sort of be able to say, oh, that's this. It's very hard to sort of be able to say, oh, that's following this particular rules, but it's still nonetheless an analog signal. Okay, and if we were to, let's say we put that into a speaker, it might sound like a G note on a guitar. Okay, so it might have a particular characteristic that means something to us, but looking on a page it's very different. Very different. Okay, so it's encoding information just in a different way. Okay, so whether that information is as a sound, or whether it's as some modulation, so for example frequency modulation or FM, or amplitude modulation or AM, they are different ways of encoding information in an analog signal like this. Now it's going to look different, and I haven't really specified a scale on either of the vertical, so the voltage, or it could be current, but generally we use voltages because it's sort of easy to work with, and the time. So this could be 1 millisecond or 1 second between these peaks. Who knows? And so that all is going to be determined by what information the signal is carrying. Okay, so analog, basically a series of ons or offs. Digital, a series of ons or offs, and analog is just a voltage that is changing over time. So it's incorporating the information into that voltage. All right. Analog electronics have to incorporate that and be able to perform some sort of function with it or operation with the analog signal. So in the same way that digital circuits, say we might have an AND gate which takes 2 digital input signals, and it's only valid if it's above a certain voltage or below a certain voltage. It only thinks that that is a digital high or digital low on the inputs, and it will produce a single output that is based on some rules that the AND gate works by. Okay, with analog signals, we will be doing stuff like amplifying. So we might have a. So I'll draw it on the board. It's pretty easier. Let's say I have my simple analog signal like this, voltage over time, and this voltage here, it might go from 20 millivolts to minus 20 millivolts. Okay, so we would say that's a peak to peak voltage of about 40 millivolts. So it's it's actually a very small signal. On a like on a multimeter or something like that, you'd probably hardly be able to measure that. Okay, so it's a very small signal, and it might be going at, so this might be 1/1000th of a second between the two peaks there. Okay, so the time between those two peaks is 1/1000th of a second, or if you like, I could fit 1,000 of these in 1 second, which would mean it's going at 1,000 cycles per second, because you can see that's a cycle there, and it would repeat itself basically forever. And so if I fit 1,000 of those in a second, that's a 1,000 hertz, 1,000 cycles per second. Okay, so here's my signal. I've actually been able to characterise my signal here. It's a sinusoid, so it looks like a sine wave for anybody who's done any maths with the trigonometric functions. It's a sinusoid there, and it's got a peak-to-peak amplitude of 40 millivolts and a frequency of 1,000 hertz, or you could say a period of 1/1000th of a second. Those two statements, the frequency and the period, they're sort of, well, the frequency is 1 divided by the period. So you can talk about one and infer what the other means. Okay, so that characterises this signal. If I were to pass this through an amplifier might then have this signal on the input, and actually I'll draw that signal for an amplifier. So this is a basic amplifier, or generalised amplifier. We're going to be looking at generalised amplifiers, and further on something called an operational amplifier. So here is my 40 millivolts peak to peak on the input, and let's say it produces a 1 volt peak to peak, and this is 1 kilohertz. Okay, so this is my input signal, and it's going to produce 1 volt peak to peak, 1 kilohertz on the output. Okay, and so what it's doing is it's taking this signal here and it's keeping the frequency the same, or the period the same. That sort of stands to reason, but it's not keeping the amplitude the same. It's making the amplitude bigger, so it's amplifying. Okay, so the amplifying signal would look basically the same, just on a different scale. Okay, so instead of having only 20 millivolts to minus 20 millivolts on the waveform there, it's got 0.5 to minus 0.5 volts. So it's much bigger, in the order of about 250 times bigger, is it? No, 25 times bigger. So quite a lot bigger from this signal to this signal. So if I were to display them on the same scale, you'd hardly even be able to see this one, and it'd sort of be wiggling around there, right? So an amplifier takes an analog signal and performs some sort of function with it, and that function is making the amplitude bigger. Okay? So that's just one example of an analog circuit. Another type of circuit is something called a filter. So a filter is another type of circuit. What it does is it actually responds differently, so it amplifies or attenuates, which is sort of the same as an amplification but with a factor that is less than 1. It can attenuate or amplify the signal, but at different frequencies the attenuation or amplification is different. Okay, so another way we can show, I can show you graphically how that might be, is with something called a frequency plot or a bode. So those two graphs I just showed you before were voltage over time. Now I'm going to do voltage over frequency. So if the frequency is on the horizontal axis and my voltage of my signal is on the vertical axis, and we would have, let's say we just measured the voltage, so that peak-to-peak voltage, at lots and lots and lots of different frequencies for our signal. And we saw that we had a signal that did something like this. Okay? So that means that all of these frequencies here, they've got roughly the same amplitude. But then at some point up here, the frequencies, the amplitudes of those frequencies started to get smaller and smaller and smaller. Okay? So if we were to split our signal into lots and lots of different frequencies, then we see that we've got lots and lots and lots of equal frequency, equal amplitude for these frequencies, and then for the high frequencies it starts to drop. Okay? And so I could say that the frequencies here, the low frequencies, are being passed, and the high frequencies are being attenuated, so basically being blocked. Okay? And so I would call this the response of a low pass filter. Right? So we'll be looking at low pass and high pass and band stop filters and how we can build those. So that is the basics of the analog circuits that we're going to be looking at. So amplification and filtering. We won't be looking at, you can do it, but we won't be looking at frequency shifting at all, or anything else like that. The first circuits that we're going to be looking at is something called an op-amp, or operational amplifier. So this is the theory notes that I'll give you in a few days. I'll get you to read it in a bit more detail when I give it to you. But basically what an op-amp does is it's an amplifier circuit. And actually I'll start with the symbol first. And it's the basis for most amplifiers. So most, like if you've got an audio amplifier, like your mini amp that you guys are building, it's the basis for that, where it takes an input signal and makes it bigger. Okay. So this is the symbol for an op-amp. Okay, now there's several pins that we've got to talk about. Okay, so we actually have two inputs on the op-amp. So if you're not already, I'll get you to copy down the symbol, and including the names. Okay, now I'll walk you through it. So maybe copy down the symbol first, and then one by one we'll talk about what each of the pins' names are and what their function is, what their role is. Okay, so it's basically a triangle with, and we conventionally have the triangle pointing to the right. It doesn't have to though. The inputs are on the flat side, there's two of them, and the output is on the pointy side, and there's one of them. And there are two vertical lines that sort of go through the whole thing. Okay, I'll start with the inputs and the outputs. Okay, so we've got a plus on one of the input pins and a minus on one of the input pins. And that tells us which one is the inverting and which one is the non-inverting. When I talk about inverting, if I have a sinusoid signal like this, so this is my input, say. If I invert that input signal, it looks like this. Basically, it's upside down. Okay? So you can think of it in one of two ways. You can think of it in when it's positive on the input, if it's inverted, it's negative. Or, and this is probably a bit more generalised, because we could have these shifted up, and that sort of ruins that idea. We could think of it when the input signal is increasing, so when it's got a positive slope, if you like, so it's going up, the voltage is increasing, then the inverted signal will have a voltage that is decreasing. Okay? But you can sort of also say, well, it just looks like it's upside down. So we could say that, and that's fine. Okay, so it's an easy way to recognise it. If you see the input signal and the output signal looking like they're upside down, then it means that it's been inverted. Okay? So what happens is, if I put a sinusoid signal on the inverting input, it would produce, so if that was my input, it would produce this output. Okay, so if my input signal went on the inverting input, the output is going to be an inverted and amplified signal. If I put it on the non-inverting input, what do you think is going to happen?
Nothing.
Well, it'll just amplify it, but it won't invert it. Okay, so it'll amplify it, so it makes it bigger, or it could actually make it smaller, but generally amplifies to make it bigger. So if I had it on the non-inverting input, then it's not going to be inverted, so the peaks, the rising of my input signal is going to line up with the rising of my output signal. Okay. Our two inputs on our signals, on our amplifier, the inverting and the non-inverting, both of those will change what the signal looks like. The output signal, or the output pin, that's reasonably self-explanatory, that is going to produce a voltage, and that voltage though has limits. Well, actually this signal has limits, and it's got a couple of different things about it. So it's going to have a limit on the voltage that it can produce. So if I wanted to, let's say I set the amplifier so that it gave a 5,000 times gain, so that the output signal was 5,000 times the voltage of the input signal, and I put a signal on the input here, that would mean that the output, so this input signal is big enough, would mean the output, let's say I put a 1 volt signal on the input here, which is reasonable, I could do that reasonably easily, that would mean that the output would want to be 5,000 volts, okay? 5,000 volts peak to peak. That's not very easy to achieve, 5,000 volts, it's actually quite lethal, but it's not going to do it. Okay, because generally these voltage pins here aren't going to be anywhere near that. So what happens is the output voltage here is going to be determined by the input signal, but limited by the positive supply, and the negative supply. Okay, so the input signal is going to determine what the output signal is going to be doing, but the output is going to be limited by the positive supply. And so what happens is, if my output signal were to try and exceed this supply voltage, let's say that was 9, plus 9 and minus 9, then what would happen is, I'll draw them on the same axis. So if let's say I had my output and it was going to go between 30 and minus 30, but my supply voltage is only 9 volts, then, so this is what the output would want to do if there was no limitation there. But what actually happens is, it follows it up until it reaches about 8 volts. Okay, so it's about 1 volt less than this positive supply pin. Okay? Unless, of course, there are some chips that you can buy that go rail to rail, so it would be, if that was 9 volts, it would be 9 volts and minus 9 volts. Okay? So some chips can do that. They're a bit expensive and not very common, and they usually have other characteristics that aren't desirable, which we'll talk about those later. So generally it's about 1 volt, so I'm going to say V plus minus 1 volt. Okay, so it's about 1 volt less than that positive supply. And so basically, if it was going to try and make it go higher than that, it just clamps it to that voltage. Okay? Oh, now it's not going to be higher than that, so I'll go down again, follow my signal. Oh, okay, minus 8 volts. Clamps it. And so effectively it's clipping the top off our waveform. So if I were to make that waveform out of a piece of paper and then run a pair of scissors along the top at that maximum voltage, maximum output voltage, then it's clipping the waveform. Okay, so it's actually called clipping. Okay, so a clip output is where the output peaks just get chopped off, basically, cut off. And so the peak to peak, the maximum peak to peak output voltage is basically 1 volt less than the maximum voltage and 1 volt more than that minimum voltage there, that negative supply. Okay. Now the other thing about them, some amplifiers are only able to provide a reasonable small current, so maybe a few tens of milliamps. Okay, so the current on the output here might not be enough to drive a big speaker. Okay, it might only be enough to drive a little buzzer, or even less. Okay, guys. All right. So the output current. So the output current may also be limited to just a few milliamps. So when you're designing your amplifier circuits, this is not for all amplifiers, I might add, but a lot of amplifier circuits, they're actually quite limited in how much current they can produce on the output. If I try and draw more current than it's wanting, than it's able to provide, then effectively what happens is the output voltage just sags until it can provide that current. Okay, and so you get a reduced output voltage, which gives you a reduced gain based on the current that's being drawn from. Okay, so just to recap, we've got an op amp. It's got 5 pins on it. There's the inverting and the non-inverting input pins, the output pin, the positive supply and the negative supply. The inverting and the non-inverting input pins effectively determine what the output signal is going to be doing, whether it's going to be an inverted signal or a non-inverted signal. The output pin provides that signal, but it's going to be limiting. It's going to be limited by the positive and negative supply voltages, and actually about 1 volt less or more than those. So within some small window, and it's also going to, depending on the amplifier, but most of them are going to have a limited current as well. So generally going to be a reasonably weak current signal, even though the voltage might be 30 volts or something. So if I had 45 volts, plus or minus 45 volts on my supply rail, I could produce 44 volts, but only at about 20 milliamps or so. Okay? So not really very powerful amplifiers, well not all of them. You can get powerful amplifiers, so so you can get amplifiers. So we've actually got 50 watt amplifiers in stock here, so they can actually produce at about 45 volts, about 0.1 of an amp or something, so pretty high. And they get quite hot, so they actually have to have heat sinks bolted onto them and all sorts of things. Alrighty. Okay, so that's sort of the basics. One other little thing I think we need to talk about is, why do we have 2 input pins? Why don't we just have 1? Okay. Now, what these amplifiers, what the op amp actually does is, it amplifies not just the signal, it amplifies the difference between the signals. Okay. So this is an important point. Right? So that down there. So an op amp amplifies the difference between. And notice I've underlined difference between there. So that's an important thing to remember here. Amplifies the difference between the voltages on the input pins. So the ratio of the output to the input voltages, look at there. So how many times bigger the output voltage is compared to the input voltage, or in this case really the difference between the input voltages, is called the gain. Okay? And the typical gain for an op amp is something in the order of a couple of million or greater. Okay? So big. So that means you really only need a difference of about 1 microvolt on here, so 1 millionth of a volt, to produce about 4 volts on the output signal there. So that output voltage is going to be a good couple of million times at least, and modern ones are in the order of 10 to 20 million times, so quite high gains just for the op amp itself. And basically what that means is that any difference on this input signal will make it so that it reaches the maximum output voltage, so clipping. Okay? When it reaches that maximum output voltage, we call that saturation. Saturated output. Okay, so saturated output or saturation means the voltage cannot increase any further. It's limited by that positive supply or the negative supply. Okay? And so an op amp just on its own means basically any small difference on that input pins will saturate it, make it just reach its maximum output or minimum output voltage. Okay? So an op amp on its own isn't particularly useful as an amplifier. It doesn't amplify the signal in any way that doesn't just give you one voltage, like the positive supply or the negative supply. So without anything connected to that, it effectively becomes a digital circuit, okay? Because it's only got one of two states. It's only going to have positive saturated output or negative saturated output. And so we can actually exploit that. And there was an exam question on that. Remember the multimeter question? It had the voltage comparator. Basically what that did, that voltage comparator, is it had one voltage on here, so let's say your ramp voltage was on this pin, and your signal, your measurement voltage, so your probe, was on this pin, and when one was higher than the other, it was saturated low. When the other was, when that changed, it saturated high. Okay, so that's what a comparator is. So we'll actually look at that in a lot more detail in this topic. So the op amp amplifies the difference between the two input pins, effectively multiplies that difference by whatever the gain is, and for an op amp without any other circuitry attached to it, that gain is massive, so millions, and then it'll produce the output voltage. So without any output voltage, without any extra circuitry, then that output voltage is basically going to be either saturated high, so the maximum output voltage, or saturated low, which is the minimum output voltage. Now, important to remember with these, the voltages on these pins, they don't have to be the same. So I could have that +9 and that 0, or +9 and -6, or 0 and -6, or something like that. It doesn't matter, as long as there is a positive voltage between the two pins. If you put them in the other way around, so if you put 9 on this one and -9 on this one, chances are it's going to go up in smoke. So don't do that. Okay, so I'm going to make a simple comparator. And what this comparator is actually going to do, it's going to be a light sensing circuit. So what it's going to do, I'm going to make it so that the light turns on when the output here. Let's put an LED on the output. Okay, so what I've done is I've drawn my op amp here in the middle, and I've got my two input pins, my output pin, and my output pin is connected to an LED to 0. So what voltage, remembering that the voltage, actually what's the maximum voltage going to be on the output here? About 8 volts, isn't it? So it's going to be between about, well, let's say it's a rail-to-rail amplifier where it goes from 0 to 9, but in reality it might go from 1 to about 8, okay? And so, actually, no, it doesn't matter. So 8 to 1 volt sort of range is going to be on the output there. But it's only going to be either one of those two voltages, because remembering basically any small difference on this input here is going to make it either saturate high or saturate low. Okay? So what voltage or which saturation state is going to make the LED light up here? Saturating high or low? Saturating high. So the 8 volts on here is going to make the output high enough so that we get an 8 volt. It's basically going to be an 8 volt across the LED resistor pair. Okay, so this is going to turn on the LED, and when it's 1 volt, does the LED light up? When it's 1 volt? No. Reason why? What's the minimum voltage for an LED to turn on roughly? About 2 volts. Okay, so for a rail-to-rail, for this amplifier, where it goes from 8 to 1 volts on the output, the LED won't light up. However, if I had a transistor on here, a transistor's base voltage is about 0.7 for it to, or actually about 0.5 for it to turn on, and so this wouldn't work if I had a transistor on here. Okay, it would always be on. Okay, because the output voltage is a minimum of 1 volt, which is still enough to turn on the transistor. So you've got to be a bit careful about that. For an LED, that's fine. I could, if I liked, wire it differently. I could wire it like this. I could wire it like that, where instead of having the current going out and down through the LED to 0, I can have the current going in from the positive. Okay? It would still work, so it can sink or source current. So the op amp can sink or source. So what that means is sourcing, meaning providing current, so I can provide a current going out of the amplifier's output pin, or it can sink, so it can pull current into it. Okay? So if it's pulling current into it, as long as the output, as long as this circuit's correct and the voltage on here is right, it can do that. Okay? So I could, if I liked, make it so that I could reverse its operation by just changing this LED orientation and what it's connected to. Okay? So, and it would work just in the opposite sense. Alright? So I'm going to go back to the original diagram. Okay? Just because that's what I had in my mind. Okay, now to make this thing saturate high or low, basically all we need is for the non-inverting input to be higher than the inverting input. Okay? So what I'm going to do is I'm going to create a voltage divider. So voltage divider, how would you recognise a voltage divider circuit? Who's testing it? That's it, 2 resistors with a voltage coming out between the middle of them. Okay, so here's my 2 resistors, and I'm actually going to connect the non-inverting input, the inverting input to that point there. Okay, so here I've got my voltage divider, just made up of 2 resistors. And if, let's say they're both 100k, doesn't matter what the value is really, but as long as if they're equal, what would be the voltage on this point here? Yep, it would be 4.5 because the resistance across here is half of the total, therefore the voltage here is half of the total. Alright, so you can think of it like that. And so if you don't believe me or if you need to check, feel free to use the voltage divider formula to find this. So I'll just put down the voltage divider formula. So V out. Okay, and in this case R1 is going to be this one. And that's going to be V out. V in. Alright? So that's what okay, so in this voltage divider formula, R1 is the voltage that the voltage is across, the output voltage is across. So in this case it's this one. Okay? And because they're the same, 100 divided by 100 plus 100, that's just a half. So the output is going to be half of the input. So 4.5 volts. And so when this voltage here is greater than 4.5 volts, greater than this one, this output here is going to be 8 volts. Okay? So we don't actually have to worry about what the gain in the amplifier is because it's sufficiently large that we're just going to say, well, basically any small difference, it's saturated. It's going to make it completely high. So we can sort of think of it in a digital sense now. It's on or off, or high or low. So if the output here, if the non-inverting input is higher than the inverting input, so higher than 4.5 in this setup, then the output's going to be saturated high, which is going to turn the LED on. Right. So that's the situation we need. We need this voltage here to be larger than this one in order for the output to saturate high. Now we're going to use an LDR. LDRs have high resistance in the dark, low resistance in the light. So let's make a pathway light, so like the light in your driveway that turns on when it gets dark enough. Okay, so it's got a little solar panel about charged up and stuff. When it gets dark enough, it automatically turns on. So we want it to turn on in the dark. So we want this voltage here to be larger in the dark, and an LDR's resistance increases in the dark. If I want to change, let's say, okay, I'll draw it. We don't know which one's the LDR yet, because one of these is going to be the LDR. Which one? So when it's increasing the resistance, let's say we increase this resistance, what happens to that voltage there? Does it increase or decrease? Otherwise, increases. Okay? So if we increase this one, the whole thing's going to increase. Okay? And so increasing this one is going to make this output here, this output voltage here, increase enough. And so that's what we want. We want this voltage here to, let's say in the light, the voltage here is going to be below 4.5 volts. And when it gets dark enough, so as it gets darker and darker and darker, this voltage here is going to increase gradually over time as it gets darker. And then eventually it's going to reach a point where it's greater than that 4.5 volts and make this thing saturate high. So if we have the LDR here, then that's what's going to happen. Okay? How do you think I can make this so that I can actually adjust it so I can control what light level it turns on at? Yep. Whereabouts?
I don't know.
Do you know what? You can't be wrong.
Can't be wrong.
No.
Okay, I'll put it where the resistors are.
Which one?
Anyone.
Anyone. It doesn't actually matter. You can put it in, change any one of these resistances. This is the nice thing about it. You can change any one of these resistances to be a variable resistor. So let's make that one, just because. Right? But it doesn't have to be that one. It could be one of these. Any one of those I can change it because any one of those will change this voltage if I adjust it. Okay, keeping everything else the same. If I change it here, that voltage is going to go up and down. If I put it here, then this voltage goes up and down, but it has the same effect. It just changes what voltage this thing makes it trigger at. But it doesn't matter because it's only looking at the difference between these voltages, and so we can put it wherever we like. So I've put it there just because, but it doesn't have to be. It could be anywhere. All right. And so this circuit here, the LDR's resistance increases as it gets darker. And so as the resistance here increases, the voltage here will increase with it. And when it gets to a certain voltage that's greater than this one, then this thing will saturate. When it saturates high, so when this is higher, it's going to saturate high, turns the LED on. Okay? And it's pretty much going to do just that. It's going to go from off to on, and it's going to be really quick because it only needs a few, like maybe 10 or 20 microvolts difference on that pin. So it only has to go from being 10 microvolts below this to 10 microvolts above this in order for it to go through the full range of the amplified output. So the non-saturated range, okay? And that's going to happen pretty quickly, all right? Okay, has anybody got any questions on this? All right, I would like you now, this is going to be an exercise for you, I'll give you 5 minutes to have a go at doing it. I would like you now to change this in some way so that instead of turning on in the dark, I'd like you to make it turn on in the light. Okay? So there are 3 ways you can do it that I can think of. I would like you to see if you can figure out all 3. All right? I think most people figured out that if you swap the position of the LDR, so basically have the LDR from the positive and the resistor to the negative on that will change the operations or invert the operation. You could also swap the 2 inputs, so instead of having the LDR voltage divider connecting to the non-inverting, you can swap it to the inverting. Or you could, as I showed you before, you could put the LED connected to positive and facing the other direction. But all 3 of those things would invert the operation, but you only need to do 1 of them. All right? If you do 2 of them, you'll be back to where you started. If you do all 3, then okay, that'll do it, but kind of wasting your time. All right, so this is called a comparator. All right.